everybody, Rachel here. Today I'm going to talk about statistical significance because if you're going to be learning about public health and clinical studies, you are definitely going to come across this concept. But prepare yourself, this is going to get complicated. Get into what statistical significance is, we should probably talk about why we need it, or something like it. Say you've come up with a hypothesis that gummy bears cause the common cold. How are you going to figure out whether or not that hypothesis is true? Well, as we talked about in the video on double blinding, the gold standard for clinical trials is the double-blind, randomized, controlled trial. So in this case, we'll get a group of people, we'll randomly put them into a treatment group that eats gummy bears and a control group that eats something that looks like gummy bears but isn't, and we'll follow them to see how many people develop colds. So at the end of the study, we'll have a lot of data, but it will all boil down to a certain percentage of the treatment group has developed colds over the course of the study, and a certain percentage of the control group has developed colds over the course of the study. Let's imagine, and I'm completely making up these numbers, that we have 450 people in our treatment group, of which 4% developed colds over the course of the study, and we have 450 people in our control group, of which 0 developed colds over the course of the study. Aha, you say, gummy bears must cause the common cold, but not so fast. How do we know that the difference in the number of people who got colds between the two groups isn't just due to chance? After all, if you look at the number of people that we observed and compare that to the number of people in the whole world, we're just talking about a sample of people. And since we're acknowledging that we're just looking at a sample, we also need to acknowledge that the people in that sample could just happen to get colds at different rates, purely by random chance. This concept that the difference between your two groups is just due to chance is called the null hypothesis. And all good science tests against the null hypothesis because any difference could always just be due to chance. Your idea, in this case that gummy bears cause the common cold, is known as the alternative hypothesis. And that name is deliberate because it's always the alternative to the null hypothesis. The null hypothesis is always the baseline assumption. Hypothesis testing determines which hypothesis, the null or the alternative, is better supported by the evidence that you've collected. For instance, in the British Doctor Study video, I talked about how those researchers tested against the null hypothesis. In their case, the null hypothesis was that the difference in the mortality rates from lung cancer between smokers and non-smokers was just due to random chance. And they tested against that null hypothesis. This testing is done in all well-conducted studies. So whenever you read about a study, look to see if they've tested against the null hypothesis. It'll probably be buried in the methods and research section of the paper, and it might not be explicitly stated, but it should still be there. If it's not, eye that study with skepticism. Hypothesis testing is just one part of determining statistical significance. Statistical significance, according to statisticians, is basically the likelihood that the relationship between two or more variables is due to something other than chance. I'll be talking about it as it relates to public health and clinical studies, of course, but it's also used in many other scientific disciplines. For instance, when physicists used the Large Hadron Collider to look for the Higgs boson particle, they used statistical significance to see if their finding was likely due to something other than chance, like the existence of the particle. But statistical significance is not the same thing as research, theoretical, clinical, or practical significance. It doesn't say anything about the importance of your result, just that your result was not likely to be due to chance. Statistical significance as a concept dates back to the early 18th century. In 1710, a Scottish physician named John Arbuthnot thought that he was seeing more boys being born in his practice than girls. So, his alternative hypothesis was that there were more male births than female births. The null hypothesis was that there was an equal probability of male and female births. To see which hypothesis was better supported by the data, Arbuthnot examined the birth records for London for the 82 years from 1629 to 1710 and tested them against the null hypothesis. For every year from 1629 to 1710, there were more male births than there were female births, a result with a probability of 1 in 4.836 times 10 to the 24th, which, well, certainly seems like statistical significance. But how do we know? Let's go back to our gummy bears. What we effectively did in our made-up study was to draw a sample of people from the total population of the world to see who developed colds. Whenever you draw a sample of a population, it's always possible that the effect that you observed, in our case, the number of people who developed colds, that this effect was simply due to the sampling process itself. In other words, the difference in the number of people who got colds between the two groups could just be because the people in the treatment group just happened to be more susceptible to getting colds than the people in the control group, or indeed in the general population. So we need to know the probability of observing an effect of this magnitude or greater, even if the null hypothesis is true. Remember, according to the null hypothesis, the test statistic, in our case, the number of people who developed colds, is completely due to random chance. So it's a variable whose values depend on outcomes of a random phenomenon. What this means is, imagine that we've drawn a sample of the population and followed them to see who developed colds. And then imagine that we've done this many, many times with different samples of people. We will get different percentages of people in our sample who developed colds each time we do this, due to random chance. If we plot those percentages on a graph, we'll get a distribution or curve under which all of our data points have been plotted. According to the central limit theorem in statistics, when a sample is obtained containing many observations, such as whether each person in the sample gets a cold, and where each of those observations doesn't depend on any other observations, and then a similar sample is obtained many times, like I talked about before, the resulting probability distribution closely approximates something that is known as the normal distribution. The normal distribution is a type of continuous probability distribution for a real-valued random variable. That's a lot of words, but you'll recognize it when you see it. It's commonly called the bell curve, although there are other types of distributions that are also bell-shaped. It's easier just to show you. The normal distribution is used to represent how data from a process, in this case the sampling process, is distributed and defined by the mean and the standard deviation. Well, the mathematics can get so complicated, but the basics are the mean and the standard deviation. The mean, or average, is the center of the data, and the standard deviation is the spread of the data. All data points within the curve are possible to be seen as a result of the sampling process, but data points that are farther from the mean are less likely to be seen. So 68% of the data points are within plus or minus 1 standard deviation from the mean, while 99.7% of the data points are within plus or minus 3 standard deviations from the mean. The classic example of the normal distribution is height in humans, although technically, like many variables in biology, it actually tends to follow a log normal distribution, where the logarithm of the variable has a normal distribution. And of course, no data in the real world perfectly follows a normal distribution, but for statistical testing purposes, this is what we often use. Partly that's because of the central limit theorem in statistics that I talked about before, and partly it's because we have to use something. The number of standard deviations that your data point is from the mean is represented by the Z-score. The Z-score equals x minus mu divided by sigma. X in this case is your data point. Mu, which is the thing that looks like a U with a scoop, is the mean, and sigma, the thing that looks like an O with a ponytail, is the standard deviation. The higher or lower a z-score is, the more unlikely the result is to have happened by chance, and the more likely that your result is meaningful. But to quantify just how meaningful, we need to use another concept, the p-value. The p-value is the probability of getting a z-score of the same magnitude or more extreme, even if the null hypothesis is true. But this has gotten long and complicated enough, so I will get into p-values next week. I hope you're starting to grasp just how difficult determining whether or not a result that you've gotten in your study is statistically significant. See you next week. I hope you enjoyed this video. If you did, and you think you'll be interested in more videos about public health, click like and subscribe. Thank you. I hope to see you soon.